Section 3.3, we're going to talk about increasing and decreasing functions. This has very similar feel to it as what we did in the last section. We're just going to be emphasizing something differently, okay? So the first thing we're going to take a look at is what we mean by increasing and decreasing in symbols. And then I'll draw pictures in a sec. Increasing, an interval on which a function has the condition that when x1 is less than x2, f of x1 is less than f of x2. All right, so in terms of a picture for this, x1's here, x2's here, and they don't necessarily have to be separated by the y-axis. It's just that the x1 is occurring before the x2. That the y value for f of x1, say it's right here, is less than the y value for f of x2. So my graph needs a little bit of a label. I'll put it on here in just a second. But here is f of x1, and here is f of x2. Sorry, it would be better if I'd drawn it a little bit bigger. So if the graph is going to be connected, which is the graphs we're looking at, these two blue dots are connected in some fashion so that the graph starts at a value that's a y value lower than where it ends on this interval. Decreasing, what do you notice on decreasing is the same in the definition? Yeah, we still have the same. Sometimes students get a little bit confused with that being, like, shouldn't it be the other way around? The answer is no. We still have an x1 less than x2. Okay, so that part's the same. The interval's the same. What's different? Yeah, f of x1 is greater than f of x2, so it's sort of flipped, right? So in some kind of a picture over here, here is f of x1 up higher, and here is f of x2 down lower. So my graph has a value right here, and then a value down here, the way that I've drawn it anyway. So it looks something like this. Now you guys know that we read graphs the same way we read English. We read from left to right. Okay, so you're left to right. And so as we're looking at the graph, we're going to be looking at the graphs in that way. So visually, you probably don't have any trouble looking at that first graph and saying increasing, because we're reading the graph from left to right, and on the bottom one, decreasing. But this is the notation that goes along with that. All right, so let's talk about how derivatives are helpful, and we have seen this happen before. This is not new information. It's just organized a little differently for us. Theorem 3.1 says that if we have a function f and it's continuous, and on part 1 we find out that the derivative is positive, then it means that the function is increasing. And part B basically says that the reverse is true. If we find out that the derivative is negative, then the function is decreasing. And we did this back in section 2.1 when we first looked at graphs. You did it on your test. We did it from the other perspective though, right? Instead of starting with the graph of the derivative, we started with the graph of the function. And we made some claims based on the function itself about what the derivative would look like. What we're doing now is we're making the reverse claims. We're saying, based on some information about the derivative, we can make some statements about the original function. And what we can use to do that is called the first derivative test. Did everybody get everything on this slide? You were good? All right. This one's got a little more writing. First derivative test. All right, so the first derivative test has a lot of pieces of information. It actually tells us things about the relationship between the original graph and the derivative, okay, using the previous theorem that we just discussed. Notice it says, suppose that f is continuous. So these kinds of things are going to fall apart if we don't have continuity. That's really important. It's continuous on the interval a, b, and c is some critical number between them, okay? So critical number, remember, means the derivative equals 0 at that point. If f prime of x is greater than 0 from a to c, and f prime of x is less than 0 from c to b, So let me draw a little picture. There's absolutely no space on the screen to draw this picture, so just try to bear with me. So this says, let me get it right. Here's an interval. Here's A. C is somewhere in between, and here's B. That's what the picture is that we start with, right? And it's saying that the derivative is positive here, and the derivative is negative here. It's telling us then that what it means is that the function f changes from increasing to decreasing. And when it does that, we have a local maximum. And you can see it, can't you? That's that sign chart that we were talking about, or that I alluded to. I can't remember if I actually talked about it or just alluded to it last time. Or maybe Sam asked about it. Maybe that's what it was. Somebody asked about it, I think is what it was last time. So we've got this part where it's increasing at the beginning and then it's decreasing at the end. So we've got a maximum in between. All right, part B, or part 2 rather, says basically the reverse is true. Instead of it being positive and then negative, it's negative and then positive. So we have the same interval set up, the same A, C, and B, but there is a negative here and there's a positive here. The negative says it is decreasing, and then it is increasing, which means we have a relative or a local minimum. It's a place where we bottom out with a valley there. And part C tells us if it's the same sign, both positives or both negatives, then we don't have a local extrema. And this is a perfect example of the graph y equal x cubed. If we were to look at this one, oops. If we were to look at this one, I'm just doing the number line point of view of it anyway. So here's A, and here's 0, and here's C, B rather. If we were to look at this one and we were to find the derivative and set it equal to 0 and test it, we'd get a positive on both of these. The graph's increasing on either side of this. Both sides it's increasing. So it means it flattens out in between, but it does not have a peak or a valley. Okay? And of course the visual picture that we all are remembering hopefully looks something like this. It's that flattening out space in between. It is increasing at the beginning, it's increasing at the end, and it flattens out in the middle. So we're going to be using these pieces of information in order to take a look and classify these relative or local max and min values. So what we're going to be able to do in this section is we're going to be able to do this without remembering prior knowledge of what graphs look like. Remember we did that with parabolas and cubics and stuff last time? And without looking and taking a look at the graph on the calculator. Not that those things can't be used, but they aren't necessary once we know this piece of information as well. So we have this as another method for actually taking a look at these. All right, so the first one that we're going to look at is the graph is the equation f of x equals negative 2x squared plus 4x plus 3. The directions say to find by hand all critical numbers and to use the first derivative test to classify each location as a local max, a local min, or neither. All right, so the kicker is the finding the critical numbers. We've done that before. That's exactly where we're starting, right? It's the kickoff like at a football game, right? So what do I do to find the critical numbers? Right, I'm going to set the derivative equal to 0. And in order to do that, I actually have to find the derivative, yeah? All right, and kind of like we talked about before, for the most part, we're working with easier to deal with functions than we were in Chapter 2. What is the derivative of negative 2x squared plus 4x plus 3? Negative 4x plus 4. Very good. And then setting that equal to 0. That's what you had mentioned, Josh, right? And then we're going to solve this for x. What do you figure out that x equals from here? 1. Does everybody agree? A little bit of algebra to get to that point, but not a lot. X equal 1. All right, so what this theorem, first derivative test, tells us, yes, Snyder? It won't be negative 1 because that would actually give me an 8 on the left and a 0 on the right. I think what you might be forgetting is that you're subtracting this 4 and then dividing by the negative 4. Yeah? Good question, though. We want to make sure we do have the right sign because if our signs are wrong, it will mess up the next step. So those signs are going to be quite important. Okay, we're going to do a number line. The number line is going to have listed on it any critical value that we found. So if we find more than 1, we have more than one location. On this one, we just had the value of 1. There it is. And we are going to pick, we did this in the last chapter, I can't remember what it was we did it for. We're just going to pick any number on either side. It doesn't matter what the number is, because all we care about is whether we get a positive value or a negative value as an answer. So it doesn't matter which number we pick. I need to pick some number over here. So somebody tell me some number that I can pick that comes before 1 on the number line. 0? I like 0. 0 is a nice number to pick. And let's pick a number on the right-hand side of 1. 2. All right. Now here's the trick. You have to know what you're using to plug this number back into. Take a look at that first derivative test here. The first derivative test is all about evaluating what? What was it? The derivative. Do you guys see that? It all hinges on what the derivative is doing. So as I'm taking a look at this sign chart and I'm picking these values at 0 and 2, I want to know what the derivative is doing there. I want to evaluate f prime of 0 and f prime of 2. And I recognize this is going to give me some kind of a number. I don't really care what the number is, because the first derivative test didn't have anything that dealt with numbers. It dealt with signs. Is it positive or is it negative? So let's take a look at what happens. Let's actually find the value just for the sake of having done so. If I plug in 0 into the derivative, what do I get? I get 4. Yeah, and when I say plug it into the derivative, I mean the value that I had before I set it equal to 0 part. Okay? I get a 4. Is 4 positive or negative? It is positive, you bet. How about if I plug in 2? I actually get a negative 4. Now, the fact that they're both 4 was because we've got some symmetry going on. This is a parabola. The actual original graph is a parabola. You don't always get the same number. I don't want you to think that that always happens. But the sign here is what's important, and the sign is negative. I find it helpful to draw what positive and negative mean in this sense, so you'll see me draw this every time because I'm a visual person. If you don't draw it, that's okay. But I like this. Positive means I'm going uphill, and negative means I'm going downhill. So for me, that helps because I can see when I draw those in what is happening at 1. It's a maximum. All right, and it says the location, which is kind of a loose description. I don't like that. There's lots of things about your textbook that I'm a little uncomfortable with. I think location should be a little bit more specified. So when we see location, we're just going to give it the most specific name that we can, which means in an XY ordered pair. Okay? So the X value for the location, we already found that. That's 1. How would I find the Y value for that location? Plug it into the original equation. So if I plug in f of 1, or plug in 1 into f, find f of 1, what will I get? Is it 5? Yeah? Okay, good. All right, so what we need to do is we need to actually answer the question asked. All of this is the work supporting my answer, but I have yet to actually answer anything on the problem. Okay? What is the answer? I have a maximum. What's next? At the point 1,5. That is a great way to describe that. If you wanted it to mirror what we did in the last section where I said something like we have a maximum of 5 at x equal 1, you could do that too. That'd be okay. But this is a great way of condensing that down into a point location. Okay, let's try another one. Function's a little bit more interesting, a little bit less comfortable to work with. I have x plus 4 over x, the exact same directions. Nothing's different on that. So if I'm asked to find and classify critical values, the first thing to do is what? Find the derivative. And it might be helpful before I find this particular derivative to rewrite this one in this fashion. It's not absolutely crucial, but it is a helpful way to write it. All right, so what is the derivative of x? 1, right. What's the derivative of 4x to the negative 1? I think I'm hearing it. Negative 4x to the negative 2. Is that what you guys are saying? Okay, good. Okay, what is my next step? Set it equal to 0. And I could do that from here, but I actually think it might be a little bit more helpful to rewrite it before I do that. At some point, I'm going to have to rewrite something anyway, so I'm going to rewrite it here. The 4 stays on top. Some of you like to move the 4 down with the other. The 4 doesn't have a negative exponent, so it's only the x that's going to move down to the denominator with its exponent too. And then we're going to set this equal to 0. There's at least a couple of ways that you could actually solve this at this point. So somebody give me a suggestion. Okay, I'm going to do let me describe what you did. I'm just not going to add the one. I'm going to move the other one since it's negative. Is that okay? So Cooper wants to do something like this, and then multiply by x squared. So I end up getting x squared equals 4. Is everybody okay with that option? I think that's a really good one here. Did anyone see something else that you could do? There's another way to do the problem. You could get a common denominator, and then it ends up being that the numerator is set equal to 0. You'll get the same values either way. I don't want to confuse the issue. I just want you to recognize there are more than one way. There is more than one way to solve this particular one, and it would work out. All right, so what am I going to do next? I'm at the point where I've got x squared equals 4. What's next? Take a square root. So what do I get? Oh, you guys are so good. You remembered your pluses or minuses. I'm very proud. We do get plus or minus 2. Well done. Alrighty then. There's one other critical point. Any idea what it might be? It is 0, Josh. Why did you think 0? Yeah, anytime we have denominators, they do tend to cause problems, variables and denominators. In particular, think about what you know about what happens a lot of times when you have a 0 in the denominator. What visually happens? Asymptotes. And do things change on either sides of asymptotes? They sometimes do. So we do have the potential that at x equals 0, it wouldn't give us any maxes or mins, but it could give us information about things being increasing or decreasing. Okay? So when we are moving into this section further, I think it's on the next, well, no, I can't remember. I don't have it written down quite that way. It's okay. I'll show it to you when we get to it. We also have the possibility, let me not write it here the exact same way, of asking the question, where does the derivative not exist? I mentioned this earlier, and the answer to this is, in fact, when x is equal to 0 on this one. So I do end up with 3 critical points. We do know, of course, like we said, though, that x equals 0 is not a max or a min. It's an asymptote. But all right, so when we set up our number line and we look at these values, I have 3 values, which makes life a little more interesting. 3 values. So I need to test how many values? 4, actually, don't I? So I'm going to write the values that I'm going to test in orange, just between them. What value would you like to test before negative 2? Negative 3? How about between negative 2 and 0? Negative 1? Between 0 and 2? 1. And between 2 and infinity? Or greater than 2? 3? Okay. So we're going to test these in what function? Very good. Test in the f prime of x function. So we're going to plug in each one of those numbers into f prime. So we're testing f prime of -3, f prime of -1, f prime of 1, and f prime of 3. And you can write down the values, which is what we did in the last problem, or you can write down just the signs. That's okay too. What do you get if you plug in -3 into the derivative function? What was it? 1 minus 4 ninths, okay. Which is going to be positive or negative? That's positive, right? Because 1's bigger than 4 ninths. That's my concern. What does positive derivatives mean? It's an increasing graph. I didn't write this on the last one, but it is an awareness to keep in mind. We're talking about something that's increasing. Okay, what happens when I plug in -1? I do. I get 1 minus 4 essentially, right? Which is negative. And what does a negative value mean? It's decreasing. And I'm going to put these on my graph in just a second. What about when I plug in the number 1? I have 1 minus 4 again, another negative, another decreasing. And what about when I plug in 3? I get a positive increasing again, same value. It happens to be the same values, and it's just because we've got squareds in what's going on, because we have squareds in what's going on. I said that right. Okay, so in terms of our graph, I had positive, negative, negative, positive. And like I warned you, I like to draw on my picture. So positive means I'm going up, negative means I'm going down, and then another positive means I'm going up. And the two places that matter are the places where I have a positive and a negative side by side, basically. So right here and right here. So what happens in the first place, the first green circle I did? That's a maximum. And my second green circle is a minimum. I was asked to find the locations again, too. And again, that's so vague that we're going to use that as specific, give the answer as specifically as we can. So if I've got 2 and -2 giving me maximum and minimum values, how do I find the corresponding output or y value that goes with them? Original function. So I don't have space for that on another slide. Okay, so I'm going to find out what is y of -2 and what is y of +2 when I plug this into the original function. So what do I get when I plug in -2 into the original function? I get -4. And when I plug in +2, +4. And this is one of those weird ones, and it's going to feel a little, not a little weird, it's going to feel kind of a lot weird, actually, to write this down. The answer is that I have a maximum at what point? -2, -4. And I have a minimum at what point? And the reason, sorry, I missed a negative there, -2, -4, and then +2, +4. The reason this should feel a little bit awkward is because my maximum is smaller than my minimum. So if I were finding absolute extrema, this would not fly, right? Those y values do not seem to correspond correctly. But remember, this is local or relative, which means in a small area around it, that's what's happening. All right. A couple more examples. The first one, we're going to actually use this information. We're going to move in. This is sort of a foreshadowing of things to come, if you will. I can't remember if it's the next section or 2 sections from now. We're going to do what's called curve sketching. I think it's next section. And so this is going to give us a little bit of a taste of how we use this in curve sketching. It says to find by hand all asymptotes and extrema and sketch the graph. So asymptotes, we did that back in chapter 1. Extrema, we did in chapter 3 right now. And we're going to kind of push those two features together to draw our graph. Okay? So let's find the asymptotes first. There are 3 types of asymptotes. What are they? Horizontal, vertical, and slant. All right? And they have different ways of determining if and when we should have them. Let's start with the easiest one, which is usually the easiest one is to recognize the vertical asymptotes. How do we do vertical asymptotes? Okay, did you say numerator or did you say denominator? Numerator. It's denominator, actually. That's okay. I just want to make sure that I didn't say yes and then you thought I think, yeah. So the vertical asymptotes are found where we have the denominator equal to 0. Do you guys remember that? Or is it coming back to you if you didn't remember that till I just said it? Okay. How do I find where this is equal to 0? What do I do? Factor. Thank you, Josh. I'm going to factor this. Oh, did I change it? I was just trying to make it fun. All right, plus 3. Thank you. It better be a plus 3, otherwise we're not going to be able to do the factoring. So that's probably a good thing we fixed it. All right, x minus 3, x minus 1. Is everybody good with that? Awesome. All right, so if I do that, I set each value equal to 0. Then I can solve. I've got x equals 3 and x equals 1. Are we good so far? All right, I'm going to do a graph as we go. Do I have another slide? I do. All right, I'm going to do my graph over here as we go. So I'm supposed to have a vertical asymptote at 3 and at 1. Okay, mine look dotted and not really dashed, but that's what I got. So this is at x equals 3 and x equals 1. Is everybody good so far? All right, that's vertical. Then I need to figure out horizontal or slant. Can you tell me? I mean, you don't have both. You have one or the other. Sometimes you have neither, but we do. We have horizontal. What do you remember about horizontal? Okay, it's all about powers. Good. And if my exponent on top is smaller or the same, then I get a horizontal asymptote. And these two are the same. I have a power of 2 on top, power of 2 on bottom. So what do I do to find my horizontal asymptote when they are the same? Coefficients. Good job, guys. And I write them as y equals, right? I know you would have done that, right? Absolutely. And the coefficients happen to both be 1s. So this is actually y equal 1. All right, on my graph. Here's y equal 1 right there, roughly. And here is my y equal 1 asymptote. Is that good? Okay, we did all that basically back in chapter 1. You've done all that in algebra before and those kinds of things. The extrema, that's different. That's the maximum minimum stuff that we've just been doing. That's not quite so friendly. Why? What is this function? It's a quotient, isn't it? Which means we need the quotient rule. All right, so I think I have space enough to do it, so we're going to do the quotient rule over here. So let's see if we remember the order and the correct notation and so forth for the quotient rule. What does the quotient rule say I do first? Okay, so the low value function first, right? What's on the bottom? So this is x squared minus 4x plus 3. And then d high, that's the derivative of what's on top. So what's the derivative of the numerator here? 2x, excellent. What comes next? A minus sign, well done. And then I need to do the reverse. I need the numerator, that's the x squared, and I need the derivative of the denominator. So what's the derivative of x squared minus 4x plus 3? Good, 2x minus 4. And the denominator squared is the new denominator. So x squared minus 4x plus 3 squared. Oh, I did. Thank you. X squared there. Very good. All right. I'm not going to belabor the simplifying on the top. It's not terribly difficult algebra. I think you guys can handle that piece okay. So I'm just going to jump to the numerator simplified. for the sake of time. It's negative 4x squared plus 6x. And the denominator stays the same. Or you can factor it if you want to. We've already factored it once, so we know what it factors into. Like this. What do I do once I have my derivative? Set it equal to 0. And if I've got a fraction, which I do on this one, what do I really want to set equal to 0? The numerator. Now, I do know where the denominator is equal to 0 because I did that finding asymptotes a little bit before, and those are critical points that I will need. But the numerator critical points I haven't done yet. So I need my numerator, 4x squared minus 6x, to be equal to 0. What will we do to simplify that? What was that? All right, take an x out. Can I take out a 2x, a negative 2x maybe even? Allison, is that okay? Okay. So this is going to change the signs on the inside. So this one will be 2x minus 3 equals 0. If you don't take all of that out, it's not going to hurt anything. You're going to get the same values either way. All right, so what do I get for x? X equals what? 0 and 3 halves. And this is where the sign chart's a little complicated. I have those two numbers on my sign chart, so that's fine. But that's not all I have on my sign chart. Oops. I also have the asymptote values on my sign chart. So I have one value at 0. I have a value of 1. That one actually comes next. That's from the asymptotes. I have a value of 3 halves. That's coming from the one I just found. And then I have a value of 3. Is that the other one? I think so, yeah. So I have 4 critical points, which means I'm going to test how many values? 5. It does. And they aren't especially pretty values to test because these numbers, some of them are quite close together. So tell me a number to test before 0. Negative 1. That one works fine. How about between 0 and 1? 1 half. Between 1 and 3 halves. That would be good. We could do 1.25. We'll even write it in decimal notation. Sounds good. How about between 3 halves and 3? 2's nice there. And then after 3? 4. All right. So we're going to plug those into what? The derivative, right? Because the derivative tells me what happens in between those places on the original graph, the positiveness or negativeness of things. All right, so let me fill in the details so that we can finish this one up. You actually end up getting a positive number before 0. You get a positive number between 0 and 1. A negative number between 1 and 3 halves. A negative number between 3 halves and 3. And then you get a, I think this is written down wrong. I think it's a positive number. No. It is. It's a negative number after that as well. Sorry, I have a typo somewhere and I didn't know if it affected something else later on. All right, so in terms of pictures, positive, positive, negative, negative, negative. What does this tell me? Right here is a max. And if I plug the number 1 back into the function and find y of 1, I will actually know what that maximum value is. Can you tell what it is? I didn't look like I would write that one down, actually. 1 over... What is it? Did you guys get it? What was it, Yusuf?
I think it's minus 1.
Is it negative 1? I think you're right. If I plug in 1 on top, I get a 1. If I plug in 1 on bottom, oh, I get a 0. Oh, right, because I actually have a asymptote there, don't I? That was one of my asymptote locations. I don't have a maximum there. Let's undo that really quick. Erase all that maximum notation. That's not appropriate. There's something I'm missing. What do I have missing? I probably have a sign wrong. I told you I had a mistake on something that was written down. Let me see my signs, because I didn't have you guys do it. Positive. That's what's wrong. The beginning, this one's negative. That's what happens when you're trying to go too fast. This was negative, and then it's positive. Then it's positive, negative, negative. That's actually correct. I should have looked at my picture to remember. Sorry, guys. Oh, that one was okay. All right, so this is negative, positive, positive, negative. That's better. Okay, let's try again. Here is a what? That's a minimum. Fabulous. And over here on the other one, it's a maximum. Okay. All right, we're going to stop right there. We'll finish up the graph for this next time. And we have one more question in this section.